everybody. We've been talking a lot about half-life in DL, so let's spend a few minutes just solidifying the concept of half-life and how to find it. Half-life shows up in systems that are undergoing exponential decay. These kinds of systems appear all the time in physics, so let's take a particular example: radioactive decay. Elements that are radioactive are actually changing from one substance to another as they decay. As an example, uranium decays into lead at a fixed rate. The half-life is just the amount of time it takes for half of the uranium to turn into lead. The interesting thing about this is that the half-life of a substance is constant. It doesn't depend on how much you start with. If you start with 10 kilograms of uranium, the amount of time it would take for half of that uranium to turn into lead, in other words, for the substance to be 5 kilograms of lead and 5 kilograms of uranium, is the same amount of time it would take 1 kilogram of uranium to turn into half a kilogram of lead and half a kilogram of uranium. This means that on a graph of exponential decay, it doesn't matter what time you pick for measuring the half-life, so long as the value at the final point is half the value at your initial point, the number you get should always be the same. Let's see that in practice with this graph. This could be a graph of anything that's undergoing exponential decay. Let's call the quantity that we're thinking about h, and on the x-axis we'll put the time. It doesn't matter exactly what the times are, we're just trying to get a general feel for how half-life works. In order to find the half-life of this system, let's see how long it takes for the height h to go from its initial value to half its initial value. If h naught is here, then half of h naught is about here. Let's draw in a little dotted line to check the time. We're not going to put in actual values for the time. We're just trying to see how half-life works in general. So the half-life of this system is about this long, however much time that represents. Now let's look at the next half-life. The next half-life is just the amount of time it takes for the height to go from half of h naught to a quarter of h naught. In other words, the amount of time it takes for h to half a second time. Let's do the same thing and see what we find out. The second half-life of this system is right here. Notice the time between the initial time and the first half-life is the same as the time between the first half-life and the second half-life. This is the expected behavior. The half-life is constant. It doesn't depend on how much you start with. We could do this exercise another time and see what we get. If my drawing was perfect, then the amount of time from the second half-life to the third half-life would be exactly the same as the time from the first half-life to the second half-life, and the time from the initial state to the first half-life. Unfortunately, my drawing is not perfect, but nonetheless, these time intervals are relatively close to these time intervals. Let's see briefly how we can calculate the half-life mathematically given an expression for the amount of a substance that we have. Let's suppose this equation describes how our system changes in time. It just says that the quantity that we're interested in as a function of time is equal to some initial value times e raised to the negative k times t. K is just a constant. It doesn't matter what it is because we're just going to try to do this in general. We want to know how long it takes for the value of this equation to drop to half of its initial value. So how do we do this? Well, let's plug in 1/2 of the initial value on the left-hand side of the equation and then solve for t. Here's the first thing to notice. There's an h naught in all the terms in this equation. This means that the h naught just cancels out. This is the same thing as saying that the half-life does not depend on how much you started with. Now let's solve this equation for t, which is the time it takes for this quantity to be half of its original value. Because t is in the exponent, we're going to need to use a natural log to bring it down. If you've forgotten how exponents and logarithms work together, that's fine. I'll leave a link to a video in the description with the details. And there we go. We found the half-life. It's just equal to the natural log of 2 divided by k. As we stated initially, the half-life doesn't depend in any way on how much we started with. It's always a constant for a particular process. Hopefully, you are also able to see that this was also true in the case of the fluid in the graduated cylinders.